So I want to derive the formula for how the atmospheric pressure drops off exponentially as we get higher and higher. Because if we look at the Earth, the reason we have pressure here is because there's this atmosphere over us. Gravity is pulling down on that atmosphere and we're feeling the weight of that atmosphere on top of us. And we know that weight is a force, and force divided by area is equal to pressure. And so how we're going to do this, we're going to look at one little chunk of atmosphere here, of some thickness dH. And what we know, if you're under a fluid of thickness dH, the change in pressure is equal to rho g delta H. Right? Where rho is the density of the liquid and dH is the thickness of the liquid. And what we find is for something like water, the pressure as you go deeper in the water is just equal to rho GH, the total height. And so this is 10 to the third kilograms, or a ton, per cubic meter. G is gravitational acceleration, is 10 meters per second squared, and height is whatever the depth is that you go down to. And this winds up being 10 to the fourth Pascal, or newtons per meter squared, per meter, times the depth that you go down. If you go down 10 meters, that gives you a pressure of 10 to the fifth Pascal, or 1 atmosphere. So if you want to double the pressure on you, you just go down 10 meters in water. So it's easy for water because the density of water is constant. And all I have to do is add up all the height or all the change in depth that I go down. But air is different. We know from the ideal gas law, PV equals nRT, that as we increase the pressure, the volume goes down. And that affects the density. Let's see, what is density? Density is equal to mass divided by volume. And the mass of some air is going to be equal to the number of molecules times the molecular mass. And I'll just write mass mole. And air is about 80% nitrogen, 20% oxygen. So nitrogen is 28, oxygen 32. It averages to about 29 grams per mole. So this is the mass of a bunch of air divided by its volume. And now we have, this is the number density, which is N over V. So let's put this over here. The number density, N over V, is just equal to P over RT, where R is the gas constant, 8.3 or 8.31 joules per mole Kelvin. And now we can write this, the density, in terms of the ideal gas law. It's N over V, which is P over RT, times the molecular mass. And this makes sense. We see as the pressure gets bigger, the density is going to increase because you compress the gas down. As the temperature gets bigger, the gas will expand and its density will decrease. So now we're ready to integrate up the total amount of pressure, or integrate down as the case may be. As we move upward, dP is going to equal pressure over RT times the molecular mass times the acceleration of gravity times dH. And so what we want to do is we want to integrate all of these little change in pressures as we move along distance. We know we have exponential behavior when the rate of change of something depends on the value of that quantity. And so we're going to expect exponential behavior of the pressure. In order to integrate, we bring this over to this side, and we have dP over P is equal to this quantity. And now we can integrate, up from zero height to some other height as we get higher and higher. And this is going to be natural log is equal to just this quantity, MOL. So we can solve for this given a reasonable temperature of on the order of 270 Kelvin or 300 Kelvin, and we end up with about 8.4 kilometers. And that's actually in the denominator. So when we integrate this up, we get height over 8.4 kilometers. Let me get some room up here. This again was water, which has a constant density. And that's not what we're doing. In order to solve for P, I need to raise E to this value. And now I can write pressure as a function of height is equal to E to the H over 8.4 kilometers. Now there's two problems. One is what this says is as I get higher and higher, the pressure is going to grow, right? And we know that's not true. As I get higher and higher, when I get into outer space, the pressure is 0. And so what I realized, I made my mistake here, because I said dP is equal to rho g h, and as h is positive, the pressure actually gets less. And so this needs to be negative. As you go up, this change in pressure is subtracted from your pressure. And so there's a minus here, there's a minus here, here, and there's a minus here. Now the other problem is this isn't units of pressure. This is unitless. And also I can say when height is 0, I expect the pressure to be atmospheric pressure, or about 10 to the 5th Pascal. So this is what I expect. So what I expect is a 10 to the 5th Pascal here as a coefficient. And where does that come in? Well, when you integrate, you also get a constant. So I should have an integration constant here. And so what does that mean? Well, if you're raising this side to the E, and you have a constant, you're adding it, that's the same as multiplying this by e to that constant. And so this is a coefficient that we multiply this by. And how do you solve for that? You use your boundary conditions. What's a boundary condition? Oh, I say, I know the pressure at some point. Well, I know the pressure at infinity is 0, so that doesn't help me much. But I know the pressure at height equals 0 is 10 to the 5th Pascal. So I have to put this in, and we can call that P naught is equal to 10 to the 5th Pascal. And so this is called your barometric formula. And again, we derive it by just recognizing as we move in height through a fluid, the change in pressure is rho g delta H. And what's special about air is that it's compressible. And so as the pressure gets bigger, density gets bigger.